not an electron, an atom off. Well, it turns out that we'll pull off one of the atoms along the waistline. That maximizes the space between the atoms better than if we take one of the ones above or below. So what is now the shape? To me, the shape of this thing looks like a snowman that's about to give you a hug. See it? You got the three there, and then it's got its arms out like, oh, hug me, hug me. But the chemists that came up with shapes of molecules were not so lovey-dovey, I'll see. But they didn't do too bad. This is what they thought when they saw this shape. What do you see? It's a teeter-totter, or a seesaw. See it? You got the two atoms that are down below, and it's kind of rocking on those. Now here's the image of that. It's kind of hard to see the two that are making the base of the seesaw, but that's what we call this a seesaw shape. Okay, now with that lone pair of electrons that has kind of occupied that orbital, what are the bond angles? Does that lone pair of electrons continue to spread out and affect the other angles? Well, yeah. However, the bigger the atom, the molecule gets, and the bigger the central atom, the less this thing can spread out and affect the other bonded atoms. So it doesn't give us the full 2-degree squeeze like we've seen before. We would say that the bond angle in this thing, it does squeeze, that lone pair squeezes those down, and it even squeezes those remaining 120-degree angles together. We're just going to say it's less than 90 degrees and less than 120. Less than 90, less than 120. So yeah, with the coordination number of 5, when we have to start removing atoms, when we have lone pairs, remove them from the middle plane, not the top and bottom. The top and bottom are going to stay for all of them. And we'll see that as we continue. Here's another coordination number of 5 slide. We have the formula ICl3. That structure looks like this. You have I with 3 Cls, and then you need 2 pairs of electrons on the I to have the right number of electrons. The I would have a coordination number of 5. It's got 3 bonded atoms and 2 lone pairs. That adds up to 5. So it's got the base shape of a trigonal bipyramid, but 2 of the orbitals are occupied by lone pairs. So I'm going to go back to the waistline, and I'm going to take another atom off. Boop, out it comes. Now what's the shape? That's a T shape, right? It's a T shape. In fact, we have the computer image of it. It's kind of on its side like that. But yeah, if we just turn it over, it's T shaped. So these are T shaped. What is the angle? We have a lone pair here and a lone pair here. So they do kind of spread out and put the squeeze on. But it's, again, because these central atoms are so huge, they can't really affect the angle as much as they could when the central atom was smaller. So we're just going to say less than 90 degrees. It is not a full 90-degree angle there because these lone pairs are spreading out, still repelling the remaining bonds. Well, I'm sorry about this. I got one more in the coordination number of 5. Coordination number 5 is the one that we seem to end. For this structure, this is a polyatomic ion. It's got a name. I can't remember what the name is. I3 with a -1. So the I3 with a -1, it needs 22 electrons. That means we're going to have 3 I's in a row bonded to each other. Here's our central I. The outside I's get the 3 lone pairs around them. Now there's 2, 4, 6, 8, 10, 12, 14, 16. I need 22 electrons, so I need 6 more electrons just stick them on there, the central atom. Okay, this is a polyatomic ion, so we'll do this. So look at the iodine in the middle. It's got a coordination number of 5. 3 lone pairs and 2 bonded atoms, coordination number is 5. Now we're down to this. Remember, originally this thing looked like that, trigonal bipyramid. Now we're going to take all the atoms off the waistline, and what are we left with? Linear. It's a straight line. These 3 atoms line up perfectly straight. Now it's really a snowman, isn't it? Yeah, it's a good snowman. Here is I3. Now in this model, they actually showed the lone pairs. You got a lone pair there, there, and there. They're just showing that the base shape was the trigonal bipyramid. But all 3 of these in the waistline are all gone now. They're just serving as lone pairs. Do these lone pairs now distort the straight line? They don't. They don't distort it. Because they're perfectly symmetrical. They're all kind of spreading out at the same angle. They're all 120 degrees. And so that straight line of the 3 iodines is going to be unaffected. It's going to be pushed at the same angle from both directions. So the shape is linear. There's 2 different linear shape possibilities. Angle is 120, exactly 120 degrees. I had said 120, 180 degrees. I hate to do this. I got one more coordination number for you. Yep. Coordination number 6. We saw this dot structure yesterday, SF6, sulfur hexafluoride. The SF6 molecule is going to have a coordination number of 6 because the S in the middle has these 6 F's on it. And how do these things arrange themselves? Now, this is a good one. You're going to like this one. With the S in the middle and 6 F's around it, we wind up spreading these F's around so that they're all 90 degrees from each other. You got the above and below, and then you have 4 right in the middle, and so they wind up all being 90-degree angle. Right? What a great structure. What are we going to call this thing? So all the angles are 90 degrees. Finally, we get one that's all 90 degrees. The way that we're going to analyze the shape is like this. Imagine that we're connecting all the peripheral F's. They all make triangular faces. How many triangular faces would we have in the structure? Can you count them? There are 8. 8 triangular faces. Where a tetrahedral atom molecule has 4 triangular faces, this has 8. This is called an octahedral molecule, or an octahedron. An octahedron. And for all the, I know that the dot structure is written like this, but here's the computer model of the SF6. Notice all the angles are 90. It's nice right angles. What's that? The octa part getting you? Yeah. I don't know how well I'm going to do this, but here's 1 triangular face. Here's 2. Now that one is hard to see, but there to there to there makes a triangular face. And here's 3, 4. Now those are all 4 on the top. Then we do the same thing on the bottom. 1, and then. Hope I did that wrong. There's 2. There's 3. There's 4. And then behind it there's 5. I just counted wrong. But there's 8. There's 8 triangular sides. If you count them here, 1, 2, 3, 4. and then 5, 6, 7, 8. There's 8 sides. You have to imagine the lines, though, around. That's how it is. All right, so octahedral. 2 more shapes, if you can hang on for 2 more shapes. ICl5 is going to have a coordination number of 6. The iodine in the middle is going to have ICl. Okay, so Cl, 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 like that. Yeah, looks like that. So you're going to have this nice symmetrical octahedral, but then we've got to disrupt it, and I'm going to remove the bottom one. It doesn't matter, since they're all 90 degrees from each other, it doesn't matter which one you remove. What does that leave us with? We have a central atom with 4 of the chlorines all in the same plane and then 1 up above it. You got a lone pair down here. What shape does that look like? This is our other pyramid that I warned you about. This is a square pyramid. Here's a computer model of that one. You have that square base, and then the 1 right raised up above it. So coordination number 6 with 1 lone pair is a square pyramid. Underneath this molecule is our lone pair. Keep in mind that that central atom is an iodine. Usually that central atom is a big thing that can get 6 things around it. So it is going to spread out, but it doesn't have the influence of pushing all 4 of these base chlorines together. So does it affect and squeeze these bonds? Yeah, but not 2 degrees or even probably close to it. So we're just going to say less than 90 degrees is our remaining bond angle. It will push these up a little bit. We'll say less than 90. And finally, we got 1 left. You okay with that? Oh, yeah, SQ is square plane. Square pyramid. So the last one is XCF4. XCF4 is going to have a coordination number of 6. Oh, we got a xenon compound. How cool. Xenon has 8 electrons. 4 fluorines are going to have 28 electrons. So we need 36 electrons in this thing. It's going to look like this. Now, there's 8 electrons around each fluorine. So there's 32 of the electrons. We need 4 more. We'll just put those above and below like that. So we have a coordination number of 6 on the XE with 2 lone pairs. So my square planar had 1 lone pair on it. If I remove the top atom, now this time I have just the XE in the middle and the 4 Fs in the same plane. Okay, name that shape. It's a square planar. Yep, square planar molecule. We're going to be working on these. I've got a model activity for you. You're going to be using some of these styrofoam balls and toothpicks to try to construct the shapes tomorrow. So if you're looking at this thing, man, I'm never going to get all these shapes. Well, we got to practice. So I'll have you practicing tomorrow with that. What do you think the bond angle is of the square planar? I have a lone pair here trying to spread out, a lone pair directly above it trying to spread out. Are they going to cancel out? Is the angle of these exactly 90 degrees? I think they are, yes. Yep. Check out this computer model of XEF4. I love this thing. In the purple parts look like little ghosts with the little eyes looking out. Maybe it's a ghost looking down at itself in a lake, and you can see its mirror image. All right, my friends, that's enough. We do have to talk a little bit about polarity. We'll start with that tomorrow, and then we'll do the activity. We're done.